we're going to differentiate the function f of x equals the natural log of the sine squared of x. For this, we're going to need to use the chain rule. F prime of x is equal to, now the first thing we're going to differentiate is the outside function, which is the natural log. And the derivative of the natural log is 1 over whatever is the argument of the log. And so in this case, it'll be 1 over the sine of squared of x. The chain rule says, though, now I have to differentiate by the, I need to differentiate the inside function, right? So let's look at the sine squared of x. As a reminder, the sine squared of x is the same thing as the sine of x, whole thing squared. And so in terms of nested functions here, we have the natural log on the outside, a squared in the middle, and then the sine function as the inner function. And so I'm going to make that exponent pink so we can say we have this middle function here, which is going to be 2 times whatever it's holding to the first power, and what it's holding is, of course, the sine of x. And then finally, the inner function is the sine of x. Its derivative is the cosine of x. And so what we're looking at here is 2 iterations of the chain rule. Now, since the sine function divides out with one of the factors in the denominator, we end up with f prime of x is equal to 2 times the cosine of x divided by the sine of x, which we can rewrite as f prime of x is equal to 2 times the cotangent of x. Next, same instructions, we're going to find the derivative of the function h of x is equal to the natural log of x plus the square root of x squared minus 1. That whole thing is the argument of the log. I'd like for you to go ahead and pause the video, take the derivative of this, only 1 or 2 steps, applying the chain rule, and then come back and we'll pick it up from there. All right, so we have the natural log function, which is the outside function. Inside of that, we have x plus the square root. And then inside the square root, we have the x squared minus 1. So we have 3 layers, kind of, but kind of. The derivative of the natural log is 1 over the argument. So we have 1 over x plus the square root of x squared minus 1 is what that should have said. The derivative of the argument of the log is going to be 1 for the derivative of x. And then for the derivative of the square root, we have 1 over 2 times the square root. The derivative of the inside of the square root, the radicand, since it is x squared minus 1, its derivative is 2x. Oftentimes at this point, folks will ask me, why isn't the 2x outside the pink parentheses? The answer is, that would imply that the 2x is the inside function also for the first term inside the log. But the 2x is coming about because of the radical, not because of the x. So the 2x only applies to the term that had x squared minus 1 as a nested function. This is different from the previous example because we had a triple nested function, but there weren't multiple terms. And of course, we can divide out the 2's here. Rewriting gives us h prime of x is equal to 1 plus x over the square root of x squared minus 1 divided by x plus the square root of x squared minus 1. Now what we have in the numerator is a complex fraction. Complex fractions need to be simplified. In this case, what that means is we're going to multiply numerator and denominator by the little fraction that makes it a complex fraction. So we're going to multiply numerator and denominator by x squared minus 1. The result in the numerator when we distribute that is going to be the square root of x squared minus 1 plus x, because that square root divides out. That kills the complex fraction. That was the point of the whole mess, right? In the denominator, I'm going to encourage you not to distribute. So we have x plus the square root of x squared minus 1 times the square root of x squared minus 1. Yeah, distributing would get rid of that radical for the second term there. It would pick it up in the first term, but if you step back for a moment and compare this factor in the denominator, x plus the square root of x squared minus 1, with the numerator, you'll see that we have the same thing. And so we actually can divide that out of the numerator entirely. And so h prime of x will then be 1 over the square root of x squared minus 1. The final answer has a radical in the denominator. And I like it. It's fine. Please don't rationalize denominators. Every time I teach this class, 5A, 5B, 5C, I tell students, please don't rationalize denominators. And a handful of them always do. It just makes things worse. Just get out of the habit. Stop it. We don't need to do it. I know, we taught it to you before. I'm telling you, get over it now. But I'm telling it to you with a smile. For our next example, we're looking at y is equal to the natural log of the cosecant of x minus the cotangent of x. Same instructions, we're going to differentiate. I'd like for you to go ahead, pause the video, differentiate this, and then get it as simplified as possible. The answer turns out to be really short. So see what you can do and then come back. So we see a nested function here. The derivative of the natural log will be 1 over the argument. So in the denominator, we have cosecant of x minus cotangent of x. Then we also multiply by the derivative of the inside function. Instead of making it 1 over that denominator and then another fraction, I just stacked this over in the numerator. So the derivative of the cosecant of x minus the cotangent of x is the negative cosecant of x cotangent of x plus the cosecant squared of x. Factoring out the common factor of cosecant of x leaves us with negative cotangent of x plus cosecant of x, which matches what we have in the denominator and so divides out, leaving us with the answer of y prime is equal to the cosecant of x. I told you it would be short. So to add to our list of things that we've been saying here, simplify trigonometric expressions as much as possible. And just what I'm talking about here, the list of things, it's complex fractions need to be simplified, don't rationalize denominators, simplify trigonometric expressions as much as possible. While we're at it, no negative exponents in final answers. Unless the base happens to be e, like e to the negative 2 is okay. The math folks, apparently they took a vote and said it was fine. Last thing I'll say is radicals need to be simplified. As in the square root of 50, for instance, is 5 times the square root of 2. No perfect square factors inside of radicals. It's fine if the square roots or the radicals are in the denominator, no problem. But pull out perfect square factors. Please. And all this isn't just me, this is the math folks say this is what simplified looks like.